Okay, well, we're going to get into lecture. We're going to talk about ions today. And we are going to start off with one of my favorite pictures from our Grand Canyon trip. There we go. Okay, chapter 3. So you guys should also be keeping up with the readings from the textbook. And if you don't know what you're supposed to be reading, how do you find that? You go to the syllabus, you look at the syllabus schedule, and it tells you what sections from the textbook you're supposed to be reading in that far right-hand column on the syllabus schedule. So please make sure you're doing the textbook assigned reading for each, I think it was sections like 3.1 through 3.4 for this lecture. And then we'll have some more on Thursday. Okay, Horseshoe Bend. So this is part of the Grand Canyon, obviously, but it was probably a good hour and a half drive from the campgrounds on the South Rim where you can go and camp, or a lot of the hotels and things if you're too cool to camp or camping is too ghetto for you. You need a bed with a mattress on it, a real mattress. So it's about an hour and a half drive, and you can see why it's called Horseshoe Bend, because the water flows around this particular portion of rock like a horseshoe. So it's real awkward though. You would just pass it. You can't see it from the road that you drive on. So there's like these sand dunes everywhere. You're driving and you literally like park in a parking lot, and it's just this, there's hardly any signs. There's nothing else around. You feel like you're in the middle of nowhere, and then you kind of walk towards the sand dune and you walk over it, and then you see the canyon. Now there's no rails, okay, in this place. I always tell people this in my lectures. There's no rails. Okay, so you do with that what you want. There were people sitting on the edge. That was not me. I don't get that close to cliff edges. So be careful if you go here, because I'm going to say it one more time, there are no rails. And that really scared me. My husband was all about it, but I was like, I will not get any closer than I am. So, but it was beautiful. My camera is not a wide angle lens. You got to have like a fancy camera to get the whole thing, but I got as much as I could in this shot. But it's really, really beautiful place to go if you're at the Grand Canyon. Okay, let's talk about chemical bonds. So what have we talked about so far? We talked about matter, how to classify matter as a pure substance or a mixture. You need to know that for the exam. There's two kinds of mixtures. We've talked about atoms, how they're structured. We have talked about prefixes and conversion problems. We're going to kind of emphasize, we're going to get into atoms a little bit more today, because so far we've only talked about atoms from the standpoint of atoms that have the same number of protons and electrons. And we said those atoms are electrically neutral. And today we're going to talk about bonds, and we're going to talk about ions. Okay. All right. So let's fill this in. Chemical bonds. What is a chemical bond? First off, the reason bonds exist is because all atoms within nature desire to be in the most stable state possible. We said the noble gases are atoms on the periodic table that are very stable, and that's why they really don't care to interact with anybody else on the periodic table. They're already stable. But every atom, every element desires to be stable, and sometimes if they're not inherently stable, they'll trade electrons, or they'll do things, they'll form chemical bonds to become more stable. Okay. Now, what is a chemical bond? It is the direct result between the attraction. Between the electrical attraction. I already have the word attraction. Electrical attraction of opposite charges. Okay. The direct result between the electrical attraction. Now, what things are electrically charged in an atom? Can anybody tell me? What things are electrically charged within an atom?
Protons and electrons.
Protons and electrons. These things we've already talked about how they're attracted. Okay, the nucleus of every atom is positively charged, and the electrons in every atom is attracted to its own nucleus. But okay, so that's this cute picture here. Look at the picture below it. This is actually a more technical picture. We have two atoms, okay, and you see the nucleus in each atom, and then you see two energy shells, two circles around each atom, the nucleus. And what's happening? This right here with an arrow coming out of it, this is a valence electron, okay? On one atom, what is it doing? It's jumping ship. It's trading atoms, okay? Because not only is it attracted, there's an attraction force between that electron and its own nucleus. But guess what? If you bring in another atom close enough, there is now attraction between that electron and the nucleus of another atom. Okay, there's attractions all different ways, okay, because this is negatively charged and this over here is positively charged as well, and that electron feels that. And if it gets close enough and if the pull is strong enough, that electron will jump over to the other atom. So electrons can trade. We talked about this last Thursday. We said how they can trade their valence electrons, and that's what you see happening here. This atom on the left is trading, or instead of trading, I'm going to say it's losing a valence electron. All right, that's what's happening here. And this atom right here is gaining a valence electron. And when that happens, these atoms, they form a chemical bond. Okay, when you trade electrons or when you give and receive, you're forming a chemical bond. Okay, now there's many compounds we know that do this. One atom completely loses its valence electron, the other atom completely gains. It's a total trade. There's no halfway point. Many chemical compounds that do this. Here's an example of one. We actually talked about this last Thursday, or I don't remember if it was Tuesday when we watched all those videos. Y'all know what's on this dish right here, right? This is salt. Now, we said salt is obviously a very docile, edible compound. It's an ionic compound. And it's made from sodium. Okay, here's our sodium metal. And in this tube, anybody know what's in this tube? It's kind of a greenish colored.
Chlorine.
Chlorine, it's a gas, right? This is chlorine gas. So this is our sodium metal, chlorine gas. Now look at these two reacting. I put a link in the lecture slides from last week. Look at what happens. There is fire here, there is smoke. That sodium metal is totally on fire just when you expose it to the gas. Okay, you don't have to do anything else. And what does it form? It forms this salt. And what's happening, the reason that this chunk of metal is on fire is because electrons, they're jumping from one atom to another. They're jumping from your sodium atoms to your chlorine atoms. And that is creating all this stuff that we see in this beaker. Okay, so it's pretty amazing to watch these things happen. And then the product that it results in, it's amazing how we can eat it. Okay, so however, when we talk about electrons going from one atom to another, we no longer have electrically neutral atoms. Now what we have, we call a compound like salt, we call it an ionic compound. Why? Because once you form these compounds, once you trade electrons, something gives it away, something receives it, you have ions. We don't have atoms anymore, electrically neutral atoms. We have ions that now have a positive or negative charge. Okay, we'll talk about what an ion is in a minute. But first, before I really get into ions, why do we even care about ions? Why are they important? Okay, well, several reasons. First off, they're important for hydration. Okay, so I put a picture of the belated Kobe Bryant. Guys, on top of everything that's happened this year, can we pause and remember that Kobe Bryant died back in January? That was like the first sign that this year was going to be crazy, right? Anyways, tribute to Kobe Bryant. He actually, I don't know if you know, had his own line of sports drinks. So a lot of you sports nutrition people, oftentimes, we tell people, especially athletes, or even people who need extra electrolytes. I have a sister-in-law. She needs a lot of salt in her diet. Okay, so she is constantly adding salt to her food because her body just needs extra salt for whatever reasons. But these sports drinks, what do they have? We call them electrolytes. Okay, but he had his own line of sports drink, and it's called Body Armor. And I was looking at it because I used to talk about Gatorade here. Okay, everybody's familiar with Gatorade. I don't know why when we're all sick, we run to the store and we get Sprite and we get Gatorade because that's got medicine in it, right? It's gonna help, but it does help us stay hydrated. If you look at this, it does have electrolytes. And in fact, Body Armor is supposed to be, Kobe Bryant's line was supposed to be healthier and better for you. One, you can look at the amount of sugars that it has. 18 grams for 8 fluid ounces, but that's half of what Gatorade offers, by the way. So it had half the amount of sugar. It's got a lot of potassium. It had more potassium than Gatorade, and it had less sodium. Okay, and honestly, less sodium most of the time is good for us. Okay. So why is this important? Why do we care about ions? Well, what happens to our bodies when we get dehydrated? Anybody know what happens if you get dehydrated? Anybody been dehydrated before?
You start cramping.
You can cramp. That's one thing
feel
that
like
can happen. You feel like what? You're going to pass out?
passing out.
Yeah. You can get like nauseous. You get very tired, fatigued. Okay. So hydration is important. So we care about ions because those are what we call electrolytes. Electrolytes and ions are the same thing. And electrolytes or ions in our body, in our cells, in our blood, they help us stay hydrated. Okay. So that's one reason we care about them. Another, here's a tribute to Powerade. They came out with a special Ion 4 is what they called it. Because Gatorade has a couple different electrolytes. It's got the potassium and the sodium. It had less calcium. I don't even know if it has magnesium in it. But they came out with this line of Powerade. And then they tried to promote it with some LeBron James. And so it's got 4 electrolytes in it when you drink that one. But these are all over the sports drinks and things like that. We care about ions for that reason. Also, ions, they have critical biological roles. Okay, what roles do they play in our body? Not only do they keep us hydrated, look at everything else they do. I'm going to zoom in real quick. Sodium, the most important thing I could say about sodium is our nerve system. Your entire nervous system, the fact that your brain is firing nerves and sending signals all over your body all the time, even while you're sleeping. We couldn't do that without sodium. Okay, so that's one. And I want you guys to be able to tell me, if I ask you on an exam, tell me 2 important roles of different ions of potassium or calcium. I would want you to be able to tell me these roles. So they help transmit nerve signals. You'll notice there's several ions involved in muscle contraction. Sodium is one of those, and it does other things. It helps us regulate the amount of water in our body. Potassium, looky there, nerve signal again. Okay, so potassium and sodium are both important for our nervous system. Again, muscle contraction, and potassium is important for the heart, which is a muscle which we know contracts all the time. Magnesium, again, muscle contraction, but also bones and teeth, and activate enzymes. What is an enzyme? Anybody know what that word means, enzyme? An enzyme is a protein, okay? So we have like 60,000 different proteins in our body. And enzymes are things that they move between cells and they help cells talk to each other, okay? So they help us perform functions like digesting our food, metabolizing our food at a decent pace, okay? Enzymes help sometimes speed things up. And so magnesium is important for that. Calcium, again, nerve signals, muscle contraction, help our bones and teeth. Calcium, what's unique to calcium is that it's important in our clotting process. For your blood to clot, if you get cut, guys, it would blow your mind how many steps there are in that process for your body just to begin to clot your blood. Calcium is critical in that, okay? And we don't see that for any of these other ions. Chlorine, we know our stomach acid is HCl, okay? So chlorine is important in the secretion of stomach acid. Also, chlorine works in tandem with sodium, NaCl, to help regulate the amount of water in our body. That's a few things chlorine does. So please know these roles. Please be able to tell me 1 or 2 of them should I ask you on the exam. I'm going to make a big deal about this as well. What do we see in this picture right here? Here's another reason ions are important.
Hemoglobin.
Hemoglobin, okay, it's a red blood cell, and this is a very cartoonish picture of hemoglobin. Hemoglobin is the protein that transports oxygen throughout your body. So no hemoglobin, no oxygen transport, and we all die, okay? So look what's in hemoglobin, though. I'm going to circle it right here. I don't know if you can see that because I try to use white. We have an ion. It is a metal. It's iron. Fe is iron. That's what contributes to the red color in red meat, okay, is iron. Red meat is high in a lot of iron. In our blood, so what colors our blood red? Iron. Rust has iron in it. Okay, we know rust is a reddish color. So anywhere you have an ion of iron, Fe, you're going to have a reddish color. So we have this iron ion in hemoglobin, and without it, we cannot transport oxygen. So it's critical for oxygen transport as well. And then lastly, I'll go back to my original color. Ions are used all the time in commercial products, and I'm just going to point out one example here. Hopefully you all brush your teeth this morning. Anybody ever left your house and you realize you forgot to brush your teeth? It's like the worst feeling ever, okay? Look right here. In toothpaste, we have fluoride ions, okay? And this is just one small example, but ions are used all the time in foods. They help preserve foods, shelf life. Here, they're used in toothpaste. So that we don't get cavities, all right? Helps protect against cavities. My sister could probably tell us more. She's a dental hygienist, so she's always asking me, do you floss? And the answer is that I don't floss as much as I should, okay? But I have a Sonicare toothbrush, and I feel like that makes up for it. She gave it to me, so there's that. All right, so we've talked about why ions are important, but what is an ion? All right, so maybe you've picked up on it by now, but it's an atom that has either lost or gained a valence electron, not just any electron. We talked about what valence electrons are. They're electrons in the outermost shell. So if I zoomed in on this picture, these atoms are not valence, but everything on the outside, these are valence. This is a valence electron, okay? But the ones on the inner circles are not. So it's an atom that has either lost or gained a valence electron and is therefore no longer electrically neutral. Okay, I want to pause on this phrase for a second because this is key to understanding. So many people get confused. What we're going to talk about the rest of lecture, understanding what kind of charge an ion will carry, whether it's a negative or positive. They get hung up on that because they don't understand this concept right here. We told you last week, we talked about the fact that a neutral atom has the same number of protons, I'm going to put a P with a plus sign, and electrons. I'm going to do an E with a minus sign. That's a neutral atom. But the second that one atom gives away an electron, now it no longer has the same number of protons and electrons. Now it's no longer electrically neutral. It's either going to have a plus charge overall or a negative charge. Okay, so if we start out with a neutral atom, look at this figure, and we lose an electron, we give one away. We are giving away something that carries a negative charge. Did we change the number of protons? No. Okay, therefore we have a positive charge overall. For example, if we start out with 10 protons and 10 electrons, this cation would now have 10 protons. How many electrons? 9 electrons. Do you see how positive 10 and negative 9 gives us what? Positive 1. Okay? You got to be able to do this kind of math. I know we're talking about molecules now and subatomic particles, but the math should be easy for you, okay? Now we have a cation. When you lose an electron and you have overall an atom, you still have an atom, but now it has a positive charge, we call that a cation. All right, and this little positive indicates to you that overall we see that atom as a positive charge. That doesn't mean it doesn't have any electrons. We still have lots of electrons. We have 9. It's just that we have one more proton than we do electrons. So overall we have a +1 charge. All right, what if we give away 2 electrons? Now we don't have 9 electrons, we're left with only 8. Oh. Okay, so now what's our cation charge? It's just a +2. Okay, so you can give away, the point I'm making here, you can give away more than 1 valence electron. You could give away 2, you could give away 3. That's going to change the charge that you have as a cation, but you'll still be a cation if you lose electrons. Let's follow this figure the other way. Let's say we gain electrons, because if you look at this figure up here, one of these atoms is losing, this one's losing, and this one is gaining an electron. So if you gain electrons, you become what we call an anion. Overall, you have a negative charge. So again, let's follow this thought. If we have 10 protons and 10 electrons, what if we gain 1 electron? Now we still have 10 protons, but we have 11 electrons. What's our charge overall? +10 and -11 gives you -1, okay? We could follow it through if we gain 2 valence electrons. If we gain 3 valence electrons, you would have a -1, a -2, or a -3 anion, okay? Questions on ions so far? Okay. All right, let's keep going. Okay, I want you to, there's a couple things on this slide that you can totally ignore. And that is these things. We were doing electron configurations, but you don't need to know any of this for what we're talking about. All right. We have a sodium ion, or atom. We have a sodium atom, okay? Na, it's a main group 1, an alkali metal, and in a regular sodium atom, we have 11 protons, all right? Now we have gone ahead, it's on row 3 of the periodic table, so we drew shell number 1, shell number 2, and shell number 3. And these numbers right here, they tell you how many electrons are in each shell. So starting out, sodium, a neutral sodium atom, has how many valence? How many valence electrons? Just 1. 1, thank you, Tucker. 1 valence electron, okay? Now, let's follow this process here. If we follow the arrow over, if we lose an electron, what happens? Well, 1, we have no electrons now in that outer shell. If you have no electrons, you don't have the shell disappears, okay? So we have decreased the size of this cation. We now have a cation because, look, we did not change the number of protons. All right, it was 11 starting out over here. We still have 11 over here. Looking at the neutral atom, we had 11 electrons. And how did we count that? We added up 2 plus 8 plus 1, the total number of electrons in sodium, and that was 11. But when we give 1 away, now we only have 10, okay? Cations are smaller than regular atoms. That's one thing you need to know. There's a trend there. Cations, they shrink down in size, often because they're losing that outer shell. And then we have an imbalance. So now when we write the cation, we write it like this. We write Na, the symbol, with a little plus charge, and it's a superscript, okay? This plus charge is what we call a super. We write it smaller and we write it up top to indicate that we don't have a neutral atom anymore. We now have an imbalance between protons and electrons. And because there's more protons than electrons, we have a single positive charge overall, okay? Where people get mixed up is because we're gaining a positive charge, but it's because we lost a negative charge. That phrase trips people up. We're gaining a positive charge because we lost a negative charge, all right? But that's what's happening. We're giving away an electron. So overall, we become positively charged because of this imbalance between protons and electrons. All right, I know I'm probably repeating myself a ton, but I'm trying to say it different ways so that it clicks. Okay, again, don't worry about any of this. And I forgot to take this off. Don't worry about this statement down here, okay? We're not talking about orbitals or electron configurations in this class. All right, let's follow through with chlorine because we started out talking about the ionic compound, sodium chloride. So we've looked at what happens with the sodium atom. Now let's talk about the chlorine atom. Here's a picture of chlorine, okay? If we go look at the periodic table, can anybody tell me what group chlorine is in? What main group?
Halogens.
Halogens. And that is main group 7, okay? Total, a chlorine, so look, on the third outer shell, we've got 7 valence electrons because it's in main group 7. But there's 2 inner shells. The second shell has 8 electrons, and the first shell has 2. Remember, I told you the first shell can only have 2 because we talked about helium and how helium is an exception to a lot of stuff because it's on that first row. Hydrogen and helium's full once it has 2 electrons, that's it. So when we add that up, 2 plus 8 plus 7, you get 17 electrons across those 3 shells. And chlorine is chlorine because of the 17 protons. Remember, the number of protons identifies the element. All right, so this is a neutral chlorine atom, and we just write Cl. No charges. We don't write a plus or a minus. Here, chlorine actually gains an electron. That's how chlorine behaves. Chlorine doesn't give away electrons, okay? Sodium you'll notice a lot of the main group 1 and 2 elements, sodium, potassium, magnesium, calcium, they like to give away electrons. We'll talk about why in a minute. Well, chlorine, main group 7, it's right next to the noble gases, okay? If I draw a periodic table, main group 7 is right next to main group 8. And remember, we said there's something very stable about having 8 valence electrons. That is stable. So if it has 7, if it just gains one more, now look, it has 8. Now it's very stable. It's like a noble gas. So the halogens, they tend to gain 1 electron. That's all they want to do to become stable, okay? If we look at sodium, same idea here. Sodium's just trying to become stable. And underneath shell 3 is shell 2, and it's got a full set of 8. So if sodium could just get rid of 1 electron, it becomes stable the way chlorine becomes stable. Okay, but when we gain electron, now we go from 17 electrons over here to 18 electrons. We did not change the number of protons. And when we add that up, 17 plus a negative 18, we get a negative 1. That's the charge now on our chlorine atom. So we write Cl with a little minus sign as a superscript. This is how we write ions. Anytime I say the word ion, it's an atom that has a charge. And you have to indicate that charge as a superscript, either a plus or a minus, or a +2 or a -2. Or you may have even noticed on some polyatomics, there's a -3, okay? Or +3 sometimes. All right, questions so far on ions and giving and trading electrons, and how we set up here, cations tend to be smaller than their neutral counterparts. Okay, neutral atom. Here, anions, they tend to get a little bit bigger, okay? All right, because they've gained an electron. Okay, before we go any further talking about ions, we're going to talk about 2 properties that are associated with different elements that are going to help us understand what kind of ion they become, either a cation or an anion. Because elements, they either become one or the other, okay? Sodium is always going to become a cation. It will never become an anion, okay? Chlorine, it will always become an anion. It will never become a cation. So why do they pick one way or the other? Well, it has to do with these properties right here. The first one is called ionization energy. We're going to talk about what that is. And the second one is electron affinity. If you read in your textbook, then you've already read about these terms, and hopefully this will just help clarify your understanding a little bit more. What is ionization energy? Okay, it is the amount of energy required for an atom to lose a valence electron, okay? Different elements, depending on how many valence they have and where they are on the periodic table, tells us that. They lose electrons more easily, or sometimes it takes a lot of energy, and it's very difficult to remove an electron from an element, okay? Some elements, they lose electrons very easily. Some of them, you got to give them a lot of energy before they'll lose an electron. So that's what ionization energy is. It's the amount of energy required to lose a valence electron. So if we look at this kind of chemical reaction that's written right next to this, and this is figure 3.2 in your textbook, by the way. This is in your textbook in case you want to look at it again. If we have an atom and we pay it, or we invest some energy, eventually if we give it enough energy, it will lose an electron, okay? What's left over, what happens when you lose an electron? You become a cation, because now you have one more proton than electron in your atom in general, and you've given off an electron. So you have a loose electron that goes usually to another atom, okay? That is ionization energy. We're going to look at a graph in just a second that helps us look at what elements have a very low, okay? low ionization energy versus what elements have a very high ionization energy and what that means. The second property is electron affinity, okay? This is the amount of energy released when an atom gains a valence electron. So it's almost just the opposite of ionization energy. If you want an atom to lose an electron, you've got to pay it some energy. If an atom's going to gain an electron, it's going to give off or give away some energy. So it's all about energy here, a trading, a receiving or a releasing of energy. So if you have an atom and it gains an electron, now you have an anion, right? We have one more electron than we do proton in the atom. And we're going to produce, that's why it's written as a product, we produce some energy. We're going to give off some energy. Okay, questions on ionization energy or electron affinity so far? All right, let's look at this graph. I'm going to turn this thing sideways. And I meant to write a bunch of poll questions, but I actually had 2 Zoom chats with students today who had questions about, different problems. And I love that. And so I didn't get to write poll questions because I was doing my Zooms this morning. So again, I just share that to say if you have questions or you feel stuck or any of this is difficult to you or you feel lost, shoot me an email. I'm not scary. I had 2 Zoom meetings this morning. They went great. So I'd love to have more. All right, let's look at this graph. The red data. We've got red data and we've got blue data. The red is our ionization energy. Okay, remember that's the amount of energy required. And you'll notice the units, it's kilojoules per mole. Okay, we haven't talked about moles yet, but we have talked about kilojoules. So we know joule is a unit of energy. Now, if we look at this red data, you notice different spikes, okay, on this data. And at the peak of every spike, let's look at the elements there because we might notice something. We notice one is helium, the next one is neon, argon, and krypton. Okay, these elements, these 4 elements have the highest ionization energies. What does that mean? We have to pay them a whole lot of energy before they would ever think about giving away an electron. Why is that? What do you know about these elements? I'll give you a tip, a hint. They're all in the same group. What main group are they in?
8.
8, yeah, and what do we call group 8?
Noble gases.
Noble gases. These are all, I'm going to put a star by them, anything with a star by it. These are our noble gases. And we said these are already stable. So it makes sense. Why in the world would they want to give away an electron if they're already stable? They don't. They don't want to give away an electron. So they're going to make their borders or their boundaries so high when it comes to ionization energy that we almost can't pay them enough energy to give away an electron. They don't want to. They want to keep the amount of electrons that they have. They've got 8 in their valence. They're stable. So that's why they have the highest ionization energies. That makes sense. All right, let's look at the elements that have at the bottom of each dip. Li, Na, K. I bet if we could look at this one over here, this would probably be cesium or francium. What elements are those?
Group 1.
Main group 1. I'm going to put a little check mark by these. Anything with a check mark? These are main group 1. Okay. These are our alkali metals. And they only have 1 valence electron. Okay. They have 1 valence electron. You notice that I abbreviate a lot, but I say what I'm writing as I abbreviate. So hopefully, if you ever get unsure about what I just wrote, please ask me. The noble gases had 8 valence electrons. Main group 1, they have the lowest ionization energy. They only have 1 valence electron. We don't have to pay them very much energy to give away that electron. Why? Because underneath they have a full set of 8. Let's go back up and look at sodium for a second. We got 1, this is a picture of sodium. If you draw the 3 circles around its nucleus, 1 valence electron. And underneath, I circled it, we said there's 8. It would love to give that 1 away because underneath it's got a full set of 8 and that's when it becomes stable. Okay, over here as a cation, full set of 8 on the outside, it's stable. So looking at that, it makes sense. Every element in group 1, same thing. It's got 1 valence. You pay it just a little bit of energy and it's happy to give away that one electron so that it becomes more stable. So they have the lowest ionization energies, okay? Also labeled on here are your halogens. And they're the next element in line close to the peak of this data, of this chart. So they also don't want to give away an electron. They want to gain an electron so that they become stable. All right. The blue data is electron affinity, okay? You guys know what the word affinity means. It's like kind of your attraction for or your desire for something. If I said I had a high affinity for ice cream, which is true, by the way, or coffee. I like coffee. I like ice cream, right? And it's the same idea here. It's kind of a measure of how much an element likes to gain an electron or wants an electron. We defined it as this. Remember, it's the amount of energy released when an atom gains a valence electron. Now, let me ask you this. If an element is releasing energy, do you think it's going to be more or less stable?
More.
More stable, okay? I have a 2-year-old. If I give her a lot of energy, and often that's in the form of sugar, okay? I had to be watching like a hawk yesterday. When we go to family's house, they love to sneak her sugar, okay? My husband's grandma's over there feeding her cookies after she already had a cookie after her lunch. And I said, Nana, no more sugar, right? Because why? She's not going to be very stable. She's going to be hyped up on sugar. When you release energy, you're more stable, okay? When you invest energy, you're less stable. So it makes sense here as we're releasing energy, these atoms, they're becoming more stable, all right? And now if you look at these, the only things that are labeled on this graph, I'm going to circle them, is fluorine, chlorine, and bromine. They have the highest electron affinities. They, the halogens, release the most energy when, they gain an electron. The halogens release the most energy. They have the highest electron affinity. They want an electron the most, and they release the most energy. They become the most stable when they get that one electron, okay? All right, that's all I wanted to point out on this graph. Any questions on what we've talked about so far? I want you to know these two properties, ionization energy, electron affinity. If I picked out 4 elements across the periodic table, in fact, we could be able to draw trends on this. I didn't leave space, did I? I'm going to try to draw a trend really quick. I think this will help because if I picked 4 elements and I said list them in order of increasing ionization energy or decreasing, or same with electron affinity, increasing electron affinity or decreasing, I would want you to be able to tell me, put those things in order. So let's draw these trends really quick. I'm going to draw a periodic table. So draw one in your notes. Okay, there's a periodic table. Close enough. Now, we said the noble gases have the highest ionization energy. The main group 1s have the lowest ionization energy. So what does that mean? As you go across the periodic table from left to right, what happens to ionization energy? I'm going to abbreviate. Ionization energy increases. Okay. Now there's also a trend here. It's not super obvious, but I noticed that lithium has a higher ionization energy than potassium. Okay, this dot right here that I just filled in is lower than this dot right here. And lithium is higher up. So as you go down the periodic table, okay, if lithium is like right up here and potassium is down here, what happens to ionization energy? It decreases. I want you to know these trends. Okay. As you go across the periodic table towards the halogens, we said they have the highest electron affinities. They want an electron the most. Okay. So that means as you go from left to right, electron, I'm going to abbreviate EA, electron affinity increases as well. Okay. Now, as you go down, I'm going to draw this one over here. What do you notice? It looks like there's not a super big trend here. But as you go down, in fact, I really can't tell. I don't really want you to worry about this one. The trend's not very obvious even from the data. So just know this one. As you go across electron affinity, it increases. Okay, so know these trends. We also talked about atomic radius and the size of elements. We drew a trend for that. Those are the 3 trends I want you to know. Here's the way I ask these questions. Put these 4 elements in order of increasing or decreasing atomic size, or ionization energy, or electron affinity, okay? And there's some practice problems on these at the end of chapter 3 that are good practice problems. Okay, questions on this? Can we do an example? Allison, here's what I'll do. I'm going to post some videos this week, and I'm going to send out that list of practice problems by the end of the day, and I will work out a problem and post a video of this to Blackboard, okay? I don't like to make up ones off the top of my head, but I'll post a video of a practice problem, okay? For sure, I'll make a note of that. All right, I'm going to introduce another new rule here. It's not necessarily a property, it's more so a rule that everything abides by when it comes to forming ions. And what this rule does, it's really important, it helps us predict the charge on ions. Okay, it's called the octet rule. What does octet mean? Octet is a word that stands for the number 8, okay? An octagon has 8 sides, okay? So the octet rule is this. It is how main group elements undergo reactions that leave them with 8 valence electrons. We said there's a magic number. Everything is more stable when they have 8. If I drew the electron dot structures for sodium and chlorine, they give away and receive electrons so that they're left with 8, okay? Now notice here, we didn't actually draw 8 around sodium, okay? Sodium has 1 valence, so we drew the electron dot structure with 1. Chlorine has 7, so we drew 7 dots around chlorine. This element jumps ship, it goes over to chlorine. So now sodium doesn't have any more valence. The 8 that it now has, if I scroll back up to that slide I showed you earlier, it's 8 on the underneath shell, okay? So we actually don't draw the 8 in on sodium anymore, we just draw the plus sign. But chlorine, now it has 8. These 2 elements are just an example of how elements react so that they're left with 8 valence electrons. So I want you to do this one on the bottom. We have element X, and this is totally a violation of how I would draw this electron dot symbol. I would draw it like this, or top and bottom, okay? So that's how, don't draw electron dot structures the way it's shown in this figure. We have element X. It has how many valence electrons? It has 2. Okay, we have element Y. It has how many valence electrons? 1, 2, 3, 4, 5, 6 dots around element Y. If these are going to react to obey the octet rule, what products would you end up with? What would I get on the other side of that arrow? I want you to draw it out in your notes really quick, and then we're going to talk about it. Draw out what you think. And remember, you're going to have ions on the other side. We have neutral atoms on this side. We're going to have ions, okay? And if you have ions, you better have a plus or a minus that represents how many electrons have been lost or received. Take a second and write out what you think. Okay, what you should have is that X, if it's going to end up with 8 in its underneath shell, it's going to give away both of those valence electrons, so that underneath it has 8. So if it gives away 2 electrons, this one is going to lose 2, lose both of those, we're going to have a +2 charge overall. It doesn't matter. Don't get lost on how many protons and electrons it now has. If it gives away 2 electrons, it's going to have a +2 charge because we didn't change the number of protons. We just lost 2 electrons. So however many protons there are, there's 2 more than the number of original electrons. And we don't draw any electrons around it, any dots, because the underneath shell is what has 8. And we only represent with the dots over here what's on the outer shell, okay? So now Y will have gained those that X lost. So these 2 are going to go over here to Y. So I'm going to draw, it had 6, 2 more means now it's going to have 8. And it was neutral over here. Now it's got 2 more electrons than it does protons, so it's going to have a -2 charge. Okay. Again, it doesn't necessarily matter for the moment. You can do this problem without knowing how many protons and electrons are in each atom. Questions on that? All right. Here's another practice problem. Okay, again, ignore this stuff right here. We have some element represented. Here's the nucleus, 8 protons, and what we see is that this particular atom has 10 electrons. It's got a full set of 8. It's undergone some sort of reaction to get enough electrons to have 8 in its outer shell. What type of atom is this? Which element? What's its overall charge? Is it a cation or an anion? And I meant to make this a poll question, but I didn't get to it. What else? So you might need to go look at a periodic table, okay? In fact, I might have one somewhere. I don't. Hopefully you have one. If you need a periodic table, look one up. Google one. If you have your textbook, open up to the front cover of your textbook. If you have lecture slides from last week, you can look in there. I've got plenty of periodic tables in there. What element is this? Which element has 8 protons? How do you identify the element? The number of protons. Okay, so which element? What's the charge? So you're going to look at the number of protons versus the number of electrons. Does that make it a cation or an anion? Anybody have an answer for us? First off, what element is it?
Oxygen.
Oxygen. Why? Because it has 8 protons, okay? If you look at the square for oxygen, now this is a periodic table that shows charges, not a normal periodic table. But you see this 8 right here. That 8 indicates the number of protons in oxygen. Remember, the number above the symbol is what is the atomic number, the number of protons. Okay, so this is oxygen. So we're going to write the symbol right there. Okay, what's the charge on this particular oxygen atom or ion?
-2.
Yes, -2. How did you get that?
8 plus -10.
There you go. We have 8 protons, so that's a +8. Plus, we have 10 electrons, so that's a -10. That gives us -2. That's the charge overall. And if it's a negative, is it a cation or an anion?
Okay.
Not a cation. Cations are when you lose electrons. Here we have gained. The neutral atom would have had 8 protons and 8 electrons. That's the neutral atom. But here we have 8 protons, 10 electrons. So it's no longer neutral. We gained 2 electrons. So this is an anion. Anions have negative charge because they've gained electrons. Cations have positive charge because they've lost electrons. Cats have paws. There we go. I like that. So what does that mean? Cations have a positive charge. Cats have paws. Okay? I like alliterations or things like that to help. I'm going to write that out. Cats, if you look in the chat if you need to, have pause, okay? Which means cations have a positive charge. Okay, so we're going to talk about a few trends. So understanding the octet rule, knowing how elements will give or receive electrons to have 8 valence, that's going to tell us what charge they're going to have. So I'm going to talk about some trends that we see with group 1, 2, 6, and 7. Okay, main group 1, 2, main group 6, and 7. So let's look at this. Main group 1A, right here. Notice all these elements, they have a +1 charge. Why? They all are metals except for hydrogen. Hydrogen is the exception here, but your main group 1 metals, so we're using an M to abbreviate whatever metal we're talking about. Here's its electron dot structure. We have 1 electron, okay? And what they do is they give away an electron because underneath they have a full set of 8. When they give away an electron, they now are a cation with a positive charge. Because they did not change the number of protons, they gave away an electron, so now you have 1 more proton than you do electron. You lost that electron, so any of these elements could be your metal that we're talking about. All right, that's what happens. So on the periodic table, main group 1, they always form a +1 charge. Now, even hydrogen abides by this rule, even though it's not a metal, because it has 1 valence, okay? And it can give away that 1 electron. It is bizarre to think it doesn't have a full set of 8 underneath, okay, the way lithium or sodium or potassium would. But it does give away that 1 valence electron. If it has 1 valence electron, it gives it away to become an ion with a +1 charge. Now let's look at what happens to group 2, main group 2. Here's the dot structure, except for remember, I wouldn't draw it there, I would draw it over here. So we got 2 valence electrons for main group 2. And if we give both of those away, we'll have a full set of 8 underneath. So when we give 2 electrons away, we become a cation with a positive charge. And we lost 2 electrons. That's any of these elements: beryllium, magnesium, calcium, strontium. Over here, the main group 2, they have a +2. What do you notice so far? The charge they tend to form as a cation matches the group numbering, and it matches the number of valence electrons they have. So this makes it real easy for you. If you're main group 1, you tend to lose that electron, you get a +1 charge. You're in main group 1, you had 1 valence, you form a +1 cation. It's just 1 all the way across the board. Number 2, same thing with group 2, okay? Transition metals are different, so we're going to skip them. I'm just pointing out the groups that are very predictable right now, and that's main group 1 and 2. They form cations with a +1 or +2 charge. Let's go over to main group 6 and 7. So group 6A, that is main group 6. An example here would be oxygen or sulfur, okay? That's this group right here. Now, they have 6 valence. So if we're applying the octet rule here, what do they want to do to get 8 valence? Do they want to lose electrons or gain?
Gain.
They want to gain. And they want to gain 2 because now if you look at the electron dot symbol, now they have a full set of 8 in their outer shell. But when they do that, the addition of 2 electrons gives them a -2 charge overall, okay? Oxygen had 8 protons. When you gain 2, now it has 10 electrons. And when you add all that up, you get -2. Same thing with sulfur. Sulfur has 16 protons and 16 electrons starting out, but when you add 2, now it will have 18 electrons. And that's an imbalance of 2, so we have -2 overall, okay? So main group 6 elements, they behave the same, all the same way, okay? They always form anions with a -2 charge. Okay, what about main group 7? So main group 7, these are halogens, fluorine, chlorine, bromine, iodine. Here's the dot structure, electron dot symbol structure, 7 dots around it, 7 valence electrons. what do they want to do? According to the octet rule, if they're going to get 8, they need to get 1 more electron. Remember, these are the elements with the highest electron affinity. So we give them 1 more electron. Okay? When we do that, let's say we're talking about fluorine here. Fluorine has 9, I don't know if you can see that, 9 protons. So if we have 9 positive charges and we add, starting out we have 9 electrons as well, but when we give it an electron, now we have 10 electrons. We had 9, we gained an electron, so now we have 10, so we have a -1 overall. And it's going to be the same idea for chlorine, bromine, and iodine. So what that means is this whole group right here, these halogens, these form anions with a -1 charge. So there are 4 main groups: main group 1, main group 2, main group 6, and main group 7 that have predictable charges. If I were you, I would have, for your exam, you're going to have a picture of a periodic table, what I call a resources page. It'll be in Blackboard. It'll be easy for you to access with your exam. If you want to print that off, that's fine as well. I'll make it available early. And I would go in and I would write +1, +2, -2, and -1 over those groups so that I remember those elements form cations or anions with those charges. They're predictable. They're always going to do that. The other groups are not always predictable. There are trends that we can tend to follow. For example, if you notice right here, aluminum, main group 3, has 3 valence, gives away 3 valence. You form a cation with a +3. All right. So there are trends that we can tend to follow, but I would go in and write these things over my periodic table to help me. Okay. Let's talk about transition metals for just a minute. We're closing in on some time here, so we'll finish whatever we don't get to on Thursday. Transition metals are different. Let's fill these blanks in. Transition metals will always lose, first off, they're metals. And metals do not become anions. I'm going to write that up here. Metals don't form anions. They form cations. And if you're a cation, that means you have lost valence electrons. So transition metals will lose their valence electrons. I forgot what that blank was supposed to be. Oh, right here. First. That's right, because sometimes they'll lose additional electrons. Transition metals have 2 valence electrons. All of them have 2 valence. They will lose those 2 first, and then sometimes they'll lose additional electrons, meaning sometimes they can form a +3 and a +4 cation. Which means sometimes they form multiple ions, cations, I should write, with unique charges. So that's your transition metals. Let's look at some examples of that. If you zoom in just on the first row, you see some. A +3. I think this is titanium right here, +4. Vanadium is a +2, but look right here. Cr, this is chromium. Also, you see the same thing with iron. They can form multiple cations. You can have an iron +2 cation. You could have an iron +3 cation. All right. Now, some of them, they don't do this. Some of them, they'll only lose like 1 or 2 electrons, and they'll have a set charge. But some of them form multiple cations with unique charges. Okay. And that's what this periodic table is showing you. The charges that they often form. Okay. Let's look at a further example of this. We have another periodic table here. I want to look at the transition metals in red. Okay, so again, your chromium, your iron, CO, this is cobalt, Cu, this is copper. These are common ions with multiple possible charges, okay? Or more than one possible charge, all right? Now, if I'm going to name these, how in the world do I know if I'm talking about the chromium +2 or the chromium +3? And what we're going to find out when we go to name these is you have to use Roman numerals. So I would say chromium 2 if I was talking about the +2 one. And I would say chromium Roman numeral 3 if I was talking about the chromium +3. We have to be able to differentiate, and we use Roman numerals to do that. So anytime, like for iron and cobalt and copper, anytime you can have more than one type of cation with a unique charge, you're going to use Roman numerals in parentheses to indicate that particular cation. Also, you'll notice mercury has 2 different cations listed, but the charge is not what's different overall. It's the number of mercury atoms involved, which is really weird. It's the only one that does this. So Hg2 +2 is not a typo. It's 2 mercury atoms, and they're locked together, and each one has a +1 charge. So we call this one, because there's 2 atoms and overall there's a +2 charge, we call it mercury 1, because each mercury atom only has a +1 charge. And because there's 2 atoms, okay, Hg +1 and Hg mercury +1, they're together. Overall, you have a +2. Don't worry about mercurius. That is kind of a different system of naming. We don't have to worry about that in this class. Okay, in blue though, these are other transition metals that invariably have 1 charge, okay, or the same charge. They either have 1 charge or the same same thing here. They don't have multiple possible cations. They just form 1 cation. And in that case, it's okay to omit the Roman numerals because you're not trying to differentiate. You're not talking about, for example, silver. Silver only forms a +1 cation. So we don't have to write silver 1. We don't have to do that because there's not a silver 2 or 3. We only have silver 1. So if you just write silver, then you're going to know it's the +1, okay? So I wanted to point that out. This makes transition metals really complex, and I get that, but you have to know that about transition metals. All right, I want to do a few practice problems. We're probably not going to get through all these because we just have 5 minutes, so let's look at just this first slide. And these should be in your notes, and so I want you to practice the ones we don't get to on your own time. And email me with questions if you have questions. Okay, how many electrons must an aluminum atom, Z, what is Z by the way? Z is the atomic number. So that means that's the number of protons. There's 13 protons here. How many electrons must it lose or gain to attain 8 valence? First off, will it lose or will it gain? It's going to go one way or the other. Remember, it's a metal. What did we write? Up here, metals don't form anions.
Total
So
gain.
that should tell you it will gain no. When you gain electrons, you form anions, right? So if metals don't form anions, they form cations. So what do you have to do to become a cation? Lose electrons. So it is going to lose how many? Well, what group is it in? Aluminum, it's already written for you. It's in main group 3. That means it has 3 valence electrons. Okay? So if it wants to have 8, it needs to lose all 3. And then underneath it has a full set of 8. Okay, so it will lose 3 valence electrons to become stable. And therefore it will form a cation. There's aluminum symbol with a +3 charge. Okay, let's do this last one and then we're done in our remaining time. Let's do this last practice problem. I want you to write the symbol for the ions formed in the following processes. Let's look at the first one. A gain of 2 electrons by selenium, Se. You don't even have to have a periodic table for these. Anybody want to say what they got? Well, first off, you're going to write Se. You gain 2 electrons. So does that mean it becomes a cation or an anion?
Anion?
An anion. Anions have negative charges overall. So if it gained 2, that's going to make it a -2. Okay, we have barium here, Ba, and it lost 2 electrons. So when you lose electrons, you become a
Cation.
cation. Mhm. Here it'll have a +2 charge. Okay, last one, we have bromine. It gained 1 electron. So how do we write it as an ion? First off, is it an anion or a cation?
Anion.
Okay. And it just gained 1 electron, so it's going to have 1 extra electron there. So it'll be a -1. Okay, I see glazed eyes.